Hello students, I am your Nandini ma'am. Today I am going to read chapter 3, Metals and Nonmetals. In class 9, you have learned about various elements. You have seen that elements can be classified as metals or nonmetals on the basis of their properties. Think of some uses of metals and nonmetals in your daily life. What properties did you think of while categorizing elements as metals or nonmetals? How are these properties related to the uses of these elements? Let us look at some of these properties in detail. Physical properties. Metals. The easiest way to start grouping substances is by comparing their physical properties. Let us study this with the help of the following activities. For performing activities 3.1 to 3.6, collect the samples of the following metals: iron, copper, aluminium, magnesium, sodium, lead, zinc, and any other metal that is easily available. Activity 3.1. Take samples of iron, copper, aluminium, and magnesium. Note the appearance of each sample. Clean the surface of each sample by rubbing them with sandpaper and note their appearance again. Metals in their pure state have a shining surface. This property is called metallic luster. Activity 3.2. Take small pieces of iron, copper, aluminium, and magnesium. Try to cut these metals with a sharp knife and note your observations. Hold a piece of sodium metal with a pair of tongs. Caution: always handle sodium metal with care. Dry it by pressing between the folds of a filter paper. Put it on a watch glass and try to cut it with a knife. What do you observe? You will find that metals are generally hard. The hardness varies from metal to metal. Activity 3.3. Take pieces of iron, zinc, and copper. Place any one metal on a block of iron and strike it 4 or 5 times with a hammer. What do you observe? Repeat with other metals. Record the change in the shape of these metals. You will find that some metals can be beaten into thin sheets. This property is called malleability. Did you know that gold and silver are the most malleable metals? Activity 3.4. List the metals whose wires you have seen in daily life. The ability of metals to be drawn into thin wires is ductility. Gold is the most ductile metal. You will be surprised to know that a wire of about 2 kilometer length can be drawn from 1 gram of gold. It is because of their malleability and ductility that metals can be given different shapes according to our needs. Can you name some metals that are used for making cooking vessels? Do you know why these metals are used for making vessels? Let us do the following activity to find out the answer. Activity 3.5. Take an aluminium or copper wire, clamp this wire on a stand as shown in figure 3.1. Fix a pin to the free end of the wire using wax. Heat the wire with a spirit lamp, candle, or a burner near the place where it is clamped. What do you observe after some time? Note your observations. Does the metal wire melt? The above activity shows that metals are good conductors of heat and have high melting points. The best conductors of heat are silver and copper. Lead and mercury are comparatively poor conductors of heat. Do metals also conduct electricity? Let us find out. Activity 3.6. Set up an electric circuit as shown in figure 3.2. Place the metal to be tested in the circuit between terminals A and B as shown. Does the bulb glow? What does this indicate? You must have seen that the wires that carry current in our homes have a coating of polyvinyl chloride, PVC, or a rubber-like material. Why are electric wires coated with such substances? What happens when metals strike a hard surface? Do they produce a sound? The metals that produce a sound on striking a hard surface are said to be sonorous. Can you now say why school bells are made of metals? Non-metals. In the previous class, you have learned that there are very few non-metals as compared to metals. Some of the examples of non-metals are carbon, sulfur, iodine, oxygen, hydrogen, etc. The non-metals are either solids or gases except bromine, which is a liquid. Do nonmetals also have physical properties similar to that of metals? Let us find out. Activity 3.7. Collect samples of carbon, coal or graphite, sulfur, and iodine. Carry out the activities 3.1 to 3.4 and 3.6 with these nonmetals and record your observations. Compile your observations regarding metals and nonmetals in Table 3.1. On the basis of the observations recorded in Table 3.1, discuss the general properties of metals and nonmetals in the class. You must have concluded that we cannot group elements according to their physical properties alone, as there are many exceptions. For example, all metals except mercury exist as solids at room temperature. In activity 3.5, you have observed that metals have high melting points, but gallium and cesium have very low melting points. These two metals will melt if you keep them on your palm. Iodine is a non-metal, but it is lustrous. Carbon is a non-metal that can exist in different forms. Each form is called an allotrope. Diamond, an allotrope of carbon, is the hardest natural substance known and has a very high melting and boiling point. Graphite, another allotrope of carbon, is a conductor of electricity. Alkali metals, lithium, sodium, potassium, are so soft that they can be cut with a knife. They have low densities and low melting points. Elements can be more clearly classified as metals and nonmetals on the basis of their chemical properties. Activity 3.8. Take a magnesium ribbon and some sulfur powder. Burn the magnesium ribbon, collect the ashes formed, and dissolve them in water. Test the resultant solution with both red and blue litmus paper. Is the product formed on burning magnesium acidic or basic? Now burn sulfur powder. Place a test tube over the burning sulfur to collect the fumes produced. Add some water to the above test tube and shake. Test this solution with blue and red litmus paper. Is the product formed on burning sulfur acidic or basic? Can you write equations for these reactions? Most nonmetals produce acidic oxides when dissolved in water. On the other hand, most metals give rise to basic oxides. You will be learning more about these metal oxides in the next section. Chemical properties of metals. We will learn about the chemical properties of metals in the following sections 3.2.1 to 3.2.4. For this, collect the samples of the following metals: aluminium, copper, iron, lead, magnesium, zinc, and sodium. What happens when metals are burnt in air? You have seen in activity 3.8 that magnesium burns in air with a dazzling white flame. Do all metals react in the same manner? Let us check by performing the following activity. Activity 3.9. Caution. The following activity needs teacher's assistance. It would be better if students wear eye protection. Hold any of the samples taken above with a pair of tongs and try burning over a flame. Repeat with the other metal samples. Collect the product if formed. Let the products and the metal surface cool down. Which metals burn easily? What flame color did you observe when the metal burnt? How does the metal surface appear after burning? Arrange the metals in the decreasing order of their reactivity towards oxygen. Are the products soluble in water? Almost all metals combine with oxygen to form metal oxides. Metal plus oxygen gives metal oxide. For example, when copper is heated in air, it combines with oxygen to form cuprous oxide, a black oxide. 2Cu plus O2 gives 2CuO. Similarly, aluminium forms aluminium oxide. 4Al plus 3O2 gives 2Al2O3. Recall from chapter 2 how copper oxide reacts with hydrochloric acid. We have learned that metal oxides are basic in nature, but some metal oxides such as aluminium oxide, zinc oxide show both acidic as well as basic behavior. Such metal oxides which react with both acids as well as bases to produce salts and water are known as amphoteric oxides. Aluminium oxide reacts in the following manner with acids and bases. Al2O3 plus 6HCl gives 2AlCl3 plus 3H2O. Al2O3 plus 2NaOH gives 2NaAlO2, which is sodium aluminate plus H2O. Most metal oxides are insoluble in water, but some of these dissolve in water to form alkalis. Sodium oxide and potassium oxide dissolve in water to produce alkalis as follows. Na2O plus H2O gives 2NaOH. K2O plus H2O gives 2KOH. We have observed in activity 3.9 that all metals do not react with oxygen at the same rate. Different metals show different reactivities towards oxygen. Metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Hence, to protect them and to prevent accidental fires, they are kept immersed in kerosene oil. At ordinary temperature, the surfaces of metals such as magnesium, aluminium, zinc, lead, etc. are covered with a thin layer of oxide. The protective oxide layer prevents the metal from further oxidation. Iron doesn't burn on heating, but iron fillings burn vigorously when sprinkled in the flame of the burner. Copper does not burn, but the hot metal is coated with a black colored layer of cuprous oxide. Silver and gold do not react with oxygen even at high temperatures. Do you know? Anodizing is a process of forming a thick oxide layer of aluminium. Aluminium develops a thin oxide layer when exposed to air. This aluminum oxide coat makes it resistant to further corrosion. The resistance can be improved further by making the oxide layer thicker. During anodizing, a clean aluminum article is made the anode and is electrolyzed with dilute sulfuric acid. The oxygen gas evolved at the anode reacts with aluminium to form a thicker protective oxide layer. This oxide layer can be dyed easily to give aluminum articles an attractive finish. After performing activity 3.9, you must have observed that sodium is the most reactive of the samples of metals taken here. The reaction of magnesium is less vigorous, implying that it is not as reactive as sodium. But burning in oxygen doesn't help us to decide about the reactivity of zinc, iron, copper, or lead. Let us see some more reactions to arrive at a conclusion about the order of reactivity of these metals. What happens when metals react with water? Activity 3.10. Caution. This activity needs teacher's assistance. Collect the samples of the same metals as in activity 3.9. Put some small pieces of the sample separately in beakers half filled with cold water. Which metals reacted with cold water? Arrange them in the increasing order of their reactivity with cold water. Did any metal produce fire on water? Does any metal start floating after some time? Put the metals that did not react with cold water in beakers half filled with hot water. For the metals that did not react with hot water, arrange the apparatus as shown in figure 3.3 and observe their reaction with steam. Which metals did not react even with steam? Arrange the metals in the decreasing order of reactivity with water. Metals react with water and produce a metal oxide and hydrogen gas. Metal oxides that are soluble in water dissolve in it to further form metal hydroxide. But all metals do not react with water. Metal plus water gives metal oxide plus hydrogen. Metal oxide plus water gives metal hydroxide. Metals like potassium and sodium react violently with cold water. In case of sodium and potassium, the reaction is so violent and exothermic that the evolved hydrogen immediately catches fire. 2K plus 2H2O gives 2KOH plus H2 plus heat energy. 2Na plus 2H2O gives 2NaOH plus H2 plus heat energy. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. Ca plus 2H2O gives CaOH whole twice plus H2. Calcium starts floating because the bubbles of hydrogen gas formed stick to the surface of the metal. Magnesium does not react with cold water. It reacts with hot water to form magnesium hydroxide and hydrogen. It also starts floating due to the bubbles of hydrogen gas sticking to its surface. Metals like aluminium, iron, and zinc do not react either with cold or hot water, but they react with steam to form the metal oxide and hydrogen. 2Al plus 3H2O gives Al2O3 plus 3H2. 3Fe plus 4H2O gives Fe3O4 plus 4H2. Metals such as lead, copper, silver, and gold do not react with water at all. What happens when metals react with acids? You have already learned that metals react with acids to give a salt and hydrogen gas. Metal plus dilute acid gives salt plus hydrogen. But do all metals react in the same manner? Let us find out. Activity 3.11. Collect all the metal samples except sodium and potassium again. If the samples are tarnished, rub them clean with sandpaper. Caution: do not take sodium and potassium as they react vigorously even with cold water. Put the samples separately in test tubes containing dilute hydrochloric acid. Suspend thermometers in the test tubes so that their bulbs are dipped in the acid. Observe the rate of formation of bubbles carefully. Which metals reacted vigorously with dilute hydrochloric acid? With which metal did you record the highest temperature? Arrange the metals in the decreasing order of reactivity with dilute acids. Write equations for the reactions of magnesium, aluminium, zinc, and iron with dilute hydrochloric acid. Hydrogen gas is not evolved when a metal reacts with nitric acid. It is because HNO3 is a strong oxidizing agent. It oxidizes the H2 produced to water and itself gets reduced to any of the nitrogen oxides, N2O, NO, NO2. But magnesium and manganese react with very dilute HNO3 to evolve hydrogen gas. You must have observed in activity 3.11 that the rate of formation of bubbles was the fastest in the case of magnesium. The reaction was almost the most exothermic in this case. The reactivity decreases in the order magnesium, then aluminium, then zinc, and then iron. In the case of copper, no bubbles were seen and the temperature also remained unchanged. This shows that copper doesn't react with dilute HCl. Do you know? Aqua Regia, Latin for royal water, is a freshly prepared mixture of concentrated hydrochloric acid and concentrated nitric acid in the ratio of 3:1. It can dissolve gold even though neither of these acids can do so alone. Aqua Regia is a highly corrosive fuming liquid. It is one of the few reagents that is able to dissolve gold and platinum. How do metals react with solutions of other metal salts? Activity 3.12. Take a clean wire of copper and an iron nail. Put the copper wire in a solution of iron sulfate and the iron nail in a solution of copper sulfate taken in test tubes. Record your observations after 20 minutes. In which test tube did you find a reaction has occurred? On what basis can you say that a reaction has actually taken place? Can you correlate your observations for the activities 3.9, 3.10, and 3.11? Write a balanced chemical equation for the reaction that has taken place. Name the type of reaction. Reactive metals can displace less reactive metals from their compounds in solution or molten form. We have seen in the previous sections that all metals are not equally reactive. We checked the reactivity of various metals with oxygen, water, and acids. But all metals do not react with these reagents. So, we were not able to put all the metal samples we had collected in decreasing order of their reactivity. Displacement reactions studied in Chapter 1 give better evidence about the reactivity of metals. It is simple and easy. If metal A displaces metal B from its solution, it is more reactive than B. Metal A plus salt solution of B gives salt solution of A plus metal B. So which metal, copper or iron, is more reactive according to your observations in activity 3.12? Reactivity series. The reactivity series is a list of metals arranged in the order of their decreasing activities. After performing displacement experiments, the following series, which is table 3.2, known as reactivity or activity series, has been developed. How do metals and nonmetals react? In the above activities, you saw the reactions of metals with a large number of reagents. Why do metals react in this manner? Let us recall what we learned about the electronic configuration of elements in class 9. We learned that noble gases which have a completely filled valence shell show little chemical activity. We therefore explain the reactivity of elements as a tendency to attain a completely filled valence shell. Let us have a look at the electronic configuration of noble gases and some metals and nonmetals. You can see from table 3.3 that a sodium atom has one electron in its outermost shell. If it loses the electron from its M shell, then its L shell now becomes the outermost shell and has an stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So there is a net positive charge giving us a sodium cation, Na+. On the other hand, chlorine has 7 electrons in its outermost shell and it requires one more electron to complete its octet. If sodium and chlorine were to react, the electron lost by sodium would be taken up by chlorine. After gaining an electron, the chlorine atom gets a unit negative charge because its nucleus has 17 protons and there are 18 electrons in its K, L and M shells. This gives us a chloride ion Cl negative. So, both these elements can have a give and take relation between them. Sodium and chloride ions, being oppositely charged, attract each other and are held by strong electrostatic forces of attraction to exist as sodium chloride, which is NaCl. It should be noted that sodium chloride does not exist as molecules but aggregates of oppositely charged ions. Let us see the formation of one more ionic compound, magnesium chloride. The compounds formed in this manner by the transfer of electrons from a metal to a nonmetal are known as ionic compounds or electrovalent compounds. Can you name the cation and anion present in MgCl2? Properties of ionic compounds. To learn about the properties of ionic compounds, let us perform the following activity. Activity 3.13. Take samples of sodium chloride, potassium iodide, barium chloride or any other salt from the science level. What is the physical state of these salts? Take a small amount of a sample on a metal spatula and heat directly on the flame. Repeat with other samples. What did you observe? Did the samples impart any color to the flame? Do these compounds melt? Try to dissolve the samples in water, petrol and kerosene. Are they soluble? Make a circuit as shown in 3.8 figure and insert the electrodes into the solution of one salt. What did you observe? Test the other salt samples too in this manner. What is your inference about the nature of these compounds? You may have observed the following general properties for ionic compounds. Physical nature. Ionic compounds are solids and are somewhat hard because of the strong force of attraction between the positive and negative ions. These compounds are generally brittle and break into pieces when pressure is applied. Melting and boiling points. Ionic compounds have high melting and boiling points. This is because a considerable amount of energy is required to break the strong inter-ionic attraction. Solubility. Electrovalent compounds are generally soluble in water and insoluble in solvents such as kerosene, petrol, etc. Conduction of electricity. The conduction of electricity through a solution involves the movement of charged particles. A solution of an ionic compound in water contains ions which move to the opposite electrodes when electricity is passed through the solution. Ionic compounds in the solid state do not conduct electricity because movement of ions in the solid is not possible due to their rigid structure. But ionic compounds conduct electricity in the molten state. This is possible in the molten state since the electrostatic forces of attraction between the oppositely charged ions are overcome due to the heat. Thus, the ions move freely and conduct electricity. Occurrence of metals. The Earth's crust is the major source of metals. Seawater also contains some soluble salts such as sodium chloride, magnesium chloride, etc. The elements or compounds which occur naturally in the Earth's crust are known as minerals. At some places, minerals contain a very high percentage of a particular metal and the metal can be profitably extracted from it. These minerals are called ores. Extraction of metals. You have learned about the reactivity series of metals. Having this knowledge, you can easily understand how a metal is extracted from its ore. Some metals are found in the Earth's crust in the free state. Some are found in the form of their compounds. The metals at the bottom of the reactivity series are the least reactive. They are often found in a free state. For example, gold, silver, platinum, and copper are found in the free state. Copper and silver are also found in the combined state as the sulfide and oxide ores. The metals at the top of the activity series are so reactive that they are never found in nature as free elements. The metals in the middle of the activity series are moderately reactive. They are found in the Earth's crust mainly as oxides, sulfides, or carbonates. You will find that ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on the Earth. Thus, on the basis of reactivity, we can group the metals into the following three categories. Metals of low reactivity, metals of medium reactivity, and metals of high reactivity. So different techniques are to be used for obtaining the metals falling in each category. Several steps are involved in the extraction of pure metal from ores. A summary of these steps is given in figure 3.10. Each step is explained in detail in the following sections. Enrichment of ores. Ores mined from the earth are usually contaminated with large amounts of impurities such as soil, sand, etc. called gangue. The impurities must be removed from the ore prior to the extraction of the metal. The processes used for removing the gangue from the ore are based on the differences between the physical or chemical properties of the gangue and the ore. Different separation techniques are accordingly employed. Extracting metals low in the activity series. Metals low in the activity series are very unreactive. The oxides of these metals can be reduced to metals by heating alone. For example, cinnabar is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide. Mercuric oxide is then reduced to mercury on further heating. Similarly, copper, which is found as CO2S in nature, can be obtained from its ore by just heating in air. Extracting metals in the middle of the activity series. Metals in the middle of the activity series such as iron, zinc, lead, copper are moderately reactive. These are usually present as sulfides or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. Therefore, prior to reduction, the metal sulfides and carbonates must be converted into metal oxides. The sulfide ores are converted into oxides by heating strongly in the presence of excess air. This process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores can be shown as follows. Roasting: 2ZnS plus 3O2 on heating gives 2ZnO plus 2SO2. Calcination: ZnCO3 on heating gives ZnO plus CO2. The metal oxides are then reduced to the corresponding metals by using suitable reducing agents such as carbon. For example, when zinc oxide is heated with carbon, it is reduced to metallic zinc. You are already familiar with the process of oxidation and reduction explained in the first chapter. Obtaining metals from their compounds is also a reduction process. Besides using carbon to reduce metal oxides to metals, sometimes displacement reactions can also be used. The highly reactive metals such as sodium, calcium, aluminium are used as reducing agents because they can displace metals of lower reactivity from their compounds. For example, manganese dioxide is heated with aluminium powder. The following reaction takes place. 3MnO2 plus 4Al gives 3Mn plus 2Al2O3 plus heat. Can you identify the substances that are getting oxidized and reduced? These displacement reactions are highly exothermic. The amount of heat evolved is so large that the metals are produced in the molten state. In fact, the reaction of ferric oxide with aluminium is used to join railway tracks or cracked machine parts. This reaction is also known as the thermite reaction. Fe2O3 plus 2Al gives 2Fe plus Al2O3 plus heat. Extracting metals towards the top of the activity series. Metals high up in the reactivity series are very reactive. They cannot be obtained from their compounds by heating with carbon. For example, carbon cannot reduce the oxides of sodium, magnesium, calcium, etc. to the respective metals. This is because these metals have more affinity for oxygen than carbon. These metals are obtained by electrolytic reduction. For example, sodium, magnesium, and calcium are obtained by the electrolysis of the molten chlorides. The metals are deposited at the cathode, which is the negatively charged electrode, whereas chlorine is liberated at the anode, which is positively charged electrode. Similarly, aluminium is obtained by the electrolytic reduction of aluminium oxide. Refining of metals. Metals produced by various reduction processes described above are not very pure. They contain impurities which must be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold, etc. are refined electrolytically. In this process, the impure metal is made the anode and a thin strip of pure metal is made the cathode. A solution of the metal salt is used as an electrolyte. The apparatus is set up as shown in figure 3.12. On passing the current through the electrolyte, the pure metal from the anode dissolves into the electrolyte. An equivalent amount of pure metal from the electrolyte is deposited on the cathode. The soluble impurities go into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. Corrosion. You have learned the following about corrosion in chapter 1. Silver articles become black after some time when exposed to air. This is because it reacts with sulfur in the air to form a coating of silver sulfide. Copper reacts with moist carbon dioxide in the air and slowly loses its shiny brown surface and gains a green coat. This green substance is basic copper carbonate. Iron, when exposed to moist air for a long time, acquires a coating of a brown flaky substance called rust. So let us find out the conditions under which iron rusts. Activity 3.14. Take 3 test tubes and place clean iron nails in each of them. Label these test tubes A, B and C and pour some water in test tube A and cork it. Pour boiled distilled water in test tube B. Add about 1 ml of oil and cork it. The oil will float on this water and prevent the air from dissolving in the water. Put some anhydrous calcium chloride in test tube C and cork it. Anhydrous calcium chloride will absorb the moisture, if any, from the air. Leave these test tubes for a few days and then observe. You will observe that iron nails rust in test tube A, but they do not rust in test tubes B and C. In the test tube A, the nails are exposed to both air and water, whereas in the test tube B, the nails are exposed to only water, while nails in test tube C are exposed to dry air only. So what does this tell us about the conditions under which iron articles rust? Prevention of corrosion. Rusting of iron can be prevented by painting, oiling, greasing, galvanizing, chrome plating, anodizing, or making alloys. Galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of zinc. Galvanized article is protected against rusting even if the zinc coating is broken. Can you reason this out? Alloying is a very good method of improving the properties of a metal. We can get the desired properties by this method. For example, iron is the most widely used metal, but it is never used in its pure state. This is because pure iron is very soft and stretches easily when hot. But if it is mixed with a small amount of carbon, it becomes hard and strong. When iron is mixed with nickel and chromium, we get stainless steel, which is hard and doesn't rust. Thus, if iron is mixed with some other substance, its properties change. In fact, the properties of any metals can be changed if it is mixed with some other substance. The substance added may be a metal or a non-metal. An alloy is a homogeneous mixture of two or more metals, or a metal and a non-metal, if it is prepared by first melting the primary metal and then dissolving the other elements in it in definite proportions. It is then cooled to room temperature. Do you know? Pure gold, known as 24-karat gold, is very soft. It is therefore not suitable for making jewelry. It is alloyed with either silver or copper to make it hard. Generally, in India, 22-karat gold is used for making ornaments. It means that 22 parts of pure gold is alloyed with 2 parts of either copper or silver. If one of the metals is mercury, then the alloy is known as an amalgam. The electrical conductivity and melting point of an alloy is less than that of pure metals. For example, brass, an alloy of copper and zinc, and bronze, an alloy of copper and tin, are not good conductors of electricity, whereas copper is used for making electrical circuits. Solder, an alloy of lead and tin, has a low melting point and is used for welding electrical wires together. More to know, the wonder of ancient Indian metallurgy. The iron pillar near the Qutub Minar in Delhi was built more than 1600 years ago by the iron workers of India. They had developed a process which prevented iron from rusting. For its quality of rust resistance, it has been examined by scientists from all parts of the world. The iron pillar is 8 meters high and weighs 6 tons. What you have learned. Elements can be classified as metals and non-metals. Metals are lustrous, malleable, ductile, and are good conductors of heat and electricity. They are solids at room temperature except mercury, which is a liquid. Metals can form positive ions by losing electrons to non-metals. Metals combine with oxygen to form basic oxides. Aluminum oxide and zinc oxide show the properties of both basic as well as acidic oxides. These oxides are known as amphoteric oxides. Different metals have different reactivities with water and dilute acids. A list of common metals arranged in order of their decreasing activity is known as an activity series. Metals above hydrogen in the activity series can displace hydrogen from dilute acids. A more reactive metal displaces a less reactive metal from its salt solution. Metals occur in nature as free elements or in the form of their compounds. The extraction of metals from their ores and then refining them for use is known as metallurgy. An alloy is a homogeneous mixture of two or more metals or a metal and a non-metal. The surface of some metals, such as iron, is corroded when they are exposed to moist air for a long period of time. This phenomena is known as corrosion. Nonmetals have properties opposite to that of metals. They are neither malleable nor ductile. They are bad conductors of heat and electricity, except for graphite, which conducts electricity. Nonmetals form negatively charged ions by gaining electrons when reacting with metals. Nonmetals form oxides, which are either acidic or neutral. Nonmetals do not displace hydrogen from dilute acids. They react with hydrogen to form hydrides. Thank you.